Okay, so problem 4.1, determine the convergent character of the following series of non-negative terms. And we have like a lot of series, like 18 of them, right? And so we're gonna go one by one, but first of all, just remember the tests that we have seen in theory for checking whether a series converges or not. And I'm gonna write them here so that we can have them as a guidance here, right? So the first one, test 1, is the comparison test, right? So remember, this is about checking that two series whose in general terms, if one general term is smaller than the other, then the convergence of the series of B sub n implies the convergence of this one, and the non-convergence or the divergence of this series implies the divergence of the second one. Then the second test is Cauchy's condensation test, which we have to test the convergence of this series 2 to the k times a to the k, sorry. Yes, so instead of testing the convergence of the original series, we test the convergence of this subseries, right? Or, well, this modified subseries, right? Now the third the third test is the limit comparison test, which has to do with series that are asymptotically equivalent or asymptotically negligible, right? So if they're asymptotically equivalent, the convergence of this one will be the same as this one, and if a sub n is asymptotically negligible with respect to b sub n, then we have the same as with the comparison test, right? Now the fourth test for series of non-negative terms is the root test. So that's compute the limit when n goes to infinity of the nth root of a sub n. Okay, and then if that's smaller than 1, the series will converge. If that's greater than 1, the series will not converge. And if it's equal to 1, then we need to check case by case, right? And the final case, the quotient, similar to the root test, but instead of checking the limit when n goes to infinity of the nth root of a sub n, is this the limit of this quotient, right? And remember that this comes from applying the Stolz theorem to this expression. Okay, so having said that and remember that, let's start with the our series. Okay, the first one is the sum from n equals 1 to infinity of n plus 1 over 2n minus 1 to the n, right? Now, this is kind of the perfect candidate for the root test. Okay, why? Because every time that the general term of a series is something that's raised or to the nth power, right? Then it's kind of easier to see what happens to the limit of the nth root of a sub n, right? Because now we just need to compute the limit of this. Okay, so in this case we have the nth the limit of the nth root of a sub n is the limit when n goes to infinity of n plus 1 over 2n minus 1. Okay, and you have been doing a lot of exercises in unit 3 from sequences, so by now you should really see that this limit is 1/2. Okay, 1/2 is smaller than 1, so this means that this series converges. Okay, this original series converges. Okay, so this is a convergent series. Okay, so remember the difference between the series, okay, and the general term of the series. Okay, okay, let's go for 2. Series number 2 is the sum from n equals 1 to infinity of 1 over 3n minus 1 squared, right? So we can do 2 tests here. We can use the comparison test, okay? The comparison test. And for the comparison test, remember remember that we have two series. One of them is the sum of 1 over n from n equals 1 to infinity, the harmonic series, which is divergent, and 1 over n squared is convergent, right? Okay, let's see, right? We have seen that in theory, so 1 over n to the alpha is convergent if alpha is greater than 1, right? So we will use these two a lot in order to compare, right? So or also in the limit comparison test, right? So as comparison, we have that 3n minus 1 squared is greater or equal than n squared, right? So then if we divide both sides by 3n minus 1 squared and n squared, we have 1 over n squared is greater or equal than 1 over 3n minus 1 squared. And this is valid for all natural numbers, right? I think. Yes. So if this is true, now we know that this series, okay, now applying the comparison test, we have bn is 1 over n squared, an is 1 over 3n minus 1 squared, and we have that a sub n is smaller than or equal than b sub n, and we know that the sum from n equals 1 to infinity of b sub n, which is this one, is smaller than infinity. So this implies, using the comparison test, that this series converges. Okay, this is convergent as well. Okay, we could also use the limit comparison test, right? So we could say, well, 3n minus 1 squared is asymptotically equivalent to 3n squared, right? Because we have this minus 1 is negligible in comparison with this, okay? And we know that 1 over 3n squared, so you could say that 1 over this is asymptotically equivalent to this, right? Now we know that this series 1 over 3 is equal to 1 over 3 times the series of 1 from n equals 1 to infinity of 1 over n squared. But this is, so this is equal, right? Not greater. Let me erase this just in case. So this is equal to 1/3 times the sum of this 1 over n squared from n equals 1 to infinity. But this is convergent, okay? So it doesn't matter that we multiply it by any number. So now, because this a sub n is asymptotically equivalent to b sub n, if this series to b sub n is convergent, then this implies that the series of a sub n is also convergent. Okay, so by using the limit comparison test, we arrive at the same conclusion as before. Okay, I think you could maybe use. I don't think the quotient test. I don't think it would lead to anything useful here. Okay, so these two, the comparison test and the limit comparison test, are very useful. Okay, in this case. Now let's see. Third, okay. This is the sum from n equals 1 to infinity of 1 over the square root of 2n to the 4th plus 1. Okay. Now, again, the easy thing to say is the square root of 2n to the 4th plus 1. This is asymptotically equivalent to the square root of 2n to the 4th, right? But this is asymptotically equivalent to square root of n times, sorry, square root of 2 times n squared, right? And again, we know that 1 over the square root, the series of this from n equals 1 to infinity of 1 over the square root of 2 times n squared is the same thing as this. And this is convergent, okay, smaller than infinity. So if these two things are asymptotically equivalent, also the fraction is asymptotically equivalent. So using the limit comparison test, this is convergent. Okay. I hope you're seeing how this works. It's not hard once you get the idea. 4. The sum from n equals 1 to infinity of 1 over the square root of n times n plus 1. That's it. Again, let's see. The square root of n times n plus 1 is equal to the square root of n squared plus n, which is asymptotically equivalent to the square root of n squared, which is equal to n. Okay, so we could say that 1 over the square root of n times n plus 1 is asymptotically equivalent to 1 over n. But the sum from n equals 1 to infinity of 1 over n is the harmonic series. It is infinity. Okay, so because these two guys are asymptotically equivalent, their convergence of their series is also equivalent. So this means that this series is divergent to plus infinity. Okay? Okay, cool. Let's go to 5. Y is the sum from n equals 1 to infinity of the absolute value of the sine of n over n squared plus n. Okay, so so let's see. First, say that n squared plus n is greater than n, right? Which implies that 1 over n is greater than 1 over n squared plus n, right? Sorry, greater than n squared and greater than n squared, right? So you can just multiply and divide both sides, you can get this. So let's use the comparison test here, right? So we have the absolute value of the sine of n divided by n squared plus n. Well, we also know that the sine of n is bounded, right? The sine is a bounded function, and it only takes values between -1 and 1. So the absolute value always takes values that are smaller than or equal than 1. Okay, so this is smaller or equal than 1 over n squared plus 1, which is smaller than 1 over n, which is just said. Okay, so we have a sub n here is smaller than b sub n here. Okay, and the sum of b sub n from n equals 1 to infinity is the sum from n equals 1 to infinity of 1 over n squared, which is smaller than infinity. So this implies that the sum of a sub n from n equals 1 to infinity, in this case a sub n here, is also smaller than infinity, or in other words, it's convergent. Okay, we get to a finite limit. Okay. Okay, let's see. 6. The sum from n equals 1 to infinity of the sine of 1 over n squared. Okay, in this case, it's clear that we need to use the limit comparison test. Okay. So in this case, the sine of 1 over n squared, as we know, the sine of epsilon sub n when epsilon goes to 0 is asymptotically equivalent to epsilon sub n. So this is asymptotically equivalent to 1 over n squared. Okay, so remember that the sine of something is asymptotically equivalent to that something when the argument is small, right? So the sine of 1 over n squared is asymptotically equivalent to 1 over n squared. And just like before, I'm not going to write everything again, right? Because the sum from n equals 1 to infinity of this is a finite value. This is also a finite value, the sum of this. Okay, so this series is convergent because this series is convergent. Okay, so this is the limit comparison test once again. Okay, let's go for 7. 7. The sum from n equals 1 to infinity of the arc sine of 1 over the square root of n. Now, okay, again, we need to use the limit comparison test. Okay, and how? Because we know that the sine of epsilon sub n is asymptotically equivalent to epsilon sub n. Okay. Well, if we take the arc sign in both sides, we can say that the arc sign is asymptotically equivalent to epsilon sub n as well, if epsilon sub n is going to 0. Okay. So yeah, this is, I mean, this is kind of not really formal, but it's easy to prove that these things are true. Okay, so you can write this down. Okay, so also if you have the tangent of epsilon sub n is asymptotically equivalent to epsilon sub n, this also means that the arc tangent of epsilon sub n is asymptotically equivalent to epsilon sub n. Okay. Okay, so having said that, then we have this. Okay. So here what we have is that the arc sign of 1 over the square root of n is asymptotically equivalent to 1 over the square root of n. Okay, but we know that the sum from n equals 1 to infinity of 1 over the square root of n is divergent. Okay, because this is 1 over n to the alpha, but alpha is 1/2, which is smaller than 1. Okay, so if alpha is smaller than 1, the series diverges. Because these two guys are asymptotically equivalent, this sum also is divergent. Okay? Okay, let's go for 8. Let's do 8. The sum from n equals 1 to infinity of 3n minus 1 over the square root of 2 to the n. Oh, so okay, this is kind of one thing that we could use. We could use either the root of the quotient, right? We have the something to the n. So let's try the root. Okay, the root test says if we have a sub n is 3n minus 1 and then square root of 2 to the n, we need to check the limit when n goes to infinity of the nth root of 3n minus 1 over this, right? Now the limit of the numerator is the limit when n goes to infinity of the nth root of 3n minus 1 divided by the square root of 2. Now this limit is going to be 1, right? Because we know that the limit of anything, the limit, the nth root of n to the p is going to be 1. Okay, the limit when n goes to infinity. Okay, this is one of the limits that we saw in the past unit. So then the result of this is 1 over the square root of 2, which is smaller than 1. Okay, 1 over the square root of 2 is 0.7 or something like that. Okay, so this means that the series is convergent. Okay, because of the root test. Okay, we could also try the quotient test. Okay, let's see how it works. Let's see the quotient test. So the quotient test tells us to test this a sub n divided by a sub n minus 1. Here a sub n is this, so we have the limit when n goes to infinity of, and then we have 3n minus 1 divided by the square root of 2 to the n, and all of this divided by this, but when the term when n equals n minus 1, right? So then this is divided by square root of 2 to the n minus 1 in the numerator, and then 3 times n minus 1 minus 1, right? So now we have the limit when n goes to infinity of, and then we have 3n minus 1 divided by 3n minus 3 minus 1, it's minus 4. Okay, times, and then here we have square root of 2 to the n minus 1 divided by the square root of 2 to the n, we have the square root of 2. in the denominator. Okay, now the limit of this we know is 1. So again, the result of this is 1 over the square root of 2, which is smaller than 1. Okay, so the quotient test also tells us that this series is convergent again, right? Okay, let's go to 9, and we're almost halfway there. Let's do 9. 9 is the sum from n equals 1 to infinity of the nth root of n minus 1 to the n. Okay, so is this true? Oh no, yes, I forgot. So this is 10. 9 is, sorry, n to the n divided by 3 to the n factorial. Okay, we could do this either using the root or the quotient. I'm going to use the root first. Okay, again, the limit when n goes to infinity of the nth root of a sub n, and a sub n is this, right? So the limit when n goes to infinity of the nth root of n to the n, 3 to the n factorial, right? And so here we have the limit when n goes to infinity, and then we have n in the numerator, 3, and the nth root of n factorial. Now, what is the nth root of n factorial? Well, here you need to apply Stirling's approximation. Okay, n factorial is approximately equal or asymptotically equivalent to n to the n, e to the minus n, the square root of 2 pi n. Okay, so I'm gonna substitute this. Okay, every time you have the factorial, it's useful to do that. So then you have n, 3 to the n, and then the nth root of this. So the nth root of n to the n is n. Oh, sorry, there's not n. It's not 3 to the n, it's just 3. And we have n, e minus 1 that goes here, okay? And then we have the square root of this, okay? This is 1, this is the nth root of this, okay? So here we have 2n, 2 times n, the nth root of that, okay? So here we have n in the numerator and n in the denominator goes out. Then we have e over 3 times the limit when n goes to infinity of 1 over the square root of 2 pi n. And that's the nth root of the square root of that. And again, the nth root of any number, it doesn't matter, it has an n in here, is 1. So this limit is 1. This is e divided by 3. But e is smaller than 3, right? So this is smaller than 1. So the root test tells us that this series is convergent. Okay? But we could also use the quotient test. Okay? Let's see how that works. Because whenever you have factorials, the quotient test works well as well. Okay, so you have the quotient test is the limit when n goes to infinity of a sub n divided by a sub n minus 1. So we have the limit when n goes to infinity of n to the n, in the denominator is 3 to the n times n factorial, and then in the numerator we have, let's see, is 3 to the n minus 1, n minus 1 factorial, and then you have n minus 1 to the n minus 1, okay? So the limit when n goes to infinity, and then we have 3 in the denominator, right? We have n minus 1 factorial divided by n factorial, so it is n in the denominator, so then we have n to the n divided by n, we have n to the n minus 1, and this is n minus 1 to the n minus 1, or in other words, this is 1/3 the limit n, sorry, when n goes to infinity, n over n minus 1 to the n minus 1. Now, as usual, this is a very typical way where you guys, or many guys, say in the exam, well, the limit of this is 1, okay? But remember, this is 1 to the infinity, right? So this is one of those limits, e to the c. But you can actually make some manipulations and say this is n minus 1 plus 1, so you have 1 plus 1 over n minus 1. Check that you can do this at home, okay? So this limit is actually the number e, okay? So again, you have e over 3 smaller than 1, okay? So the two tests, the quotient and the root, tell us that this series is convergent. Okay, let's do 10. Okay, we're almost there. 10. The sum from n equals 1 to infinity of the nth root of n minus 1 to the n. Okay, so classical root test, okay? The limit when n goes to infinity of the nth root of a sub n is the limit when n goes to infinity of the nth root of n minus 1. But the nth root of n, the limit of that is 1, so it's 1 minus 1. This is 0, smaller than 1. Okay, so the root test tells us that this series is convergent. Okay, convergent. Okay. So it's important to remember that, you know, for instance, it disappears a lot in exams. You could compute the limit of a sub n, okay, the limit of this, and so this is the limit when this is, you know, 0 to infinity, I guess, and this should go to 0, right? So this limit should go to 0, otherwise this series is not convergent, right? Well, if you know, many of you say, well, the limit of a sub n equals 0, so this is, because of this, the series is convergent, but this is not a sufficient condition, okay? You need to use one of these 5 tests, okay? So just remember that it's important to distinguish what's a sub n, the general term of a series, and then the series itself, which is the sum, okay? Okay, let's go to 11. The sum from n equals 1 to infinity of 1 plus 1 over n to the n squared times 3 to the minus n. Okay, so again, this is one of those that, you know, the first thing I would do is to use the root test, okay? And so the limit of the nth root of a sub n is the limit when n goes to infinity. So the nth root of something to the n squared is just something to the n, okay? And then you have 1 over 3. But the limit of this again is e, so then you have e over 3, which is smaller than 1. So the series again is convergent. Okay. Maybe we could try and apply the quotient test here, but you can see that it will get very, you know, troublesome very quickly. So I won't try to do it here. Okay. 12. The sum from n equals 2 to infinity of 1 over the logarithm of n to the n. Okay, so this sum starts at 2 because the logarithm of 1 is 0, so it doesn't make any sense to define this 1 over 0, right? So the series that have the logarithm in the denominator usually start in 2, right? Now again, we could use Cauchy's condensation test here, but I'm going to use the root test as well, because we have one, a sub n is 1 over the logarithm of n to the n, okay? So then the limit when n goes to infinity of the nth root of a sub n is the limit when n goes to infinity of 1 over the logarithm of n. But we know that the logarithm of n, the limit of the logarithm of n when n goes to infinity is infinity, so 1 over infinity is 0. So this is smaller than 1, the root test. And so it tells us that this series is convergent. Okay. Yeah. I think we could try and use maybe the quotient test here, but yeah, I'm not gonna do it. Okay. And so, oh yes, so it's important to see one thing. The logarithm of n to the n is not n times the logarithm of n, right? This is the logarithm of n to the n, okay? Which is not the same. So this is the logarithm of n times the logarithm of n times the logarithm of n, blah 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 blah, times the logarithm of n times, right? This is this. And then this, the logarithm of n to the n, is the logarithm of n plus the logarithm of n plus the logarithm of n plus blah blah blah, plus the logarithm of n times, okay? So please be careful with this. These two expressions are not the same, okay? These are not the same. So be careful with that. Okay, let's see. 13. The sum from n equals to infinity of n squared over the logarithm of n to the n. And again, this looks like something that you would use the root test, okay, for. So the root test, the limit when n goes to infinity of the nth root of a sub n is equal to the limit when n goes to infinity of the nth root of n squared, and we know this is going to be 1, divided by the logarithm of n. Okay, so the limit of the numerator is 1, and the limit of the denominator is infinity. So then we have 1 divided by infinity again, so 0, which is smaller than 1. Okay, so again, this series is convergent. Okay, let's keep going. Let's see, 14. The sum from n equals 1 to infinity of the square root of n squared plus 1 minus n. Now this is one of those things that we actually don't know how to deal with at the beginning, but then you can, this is a sub n, the square root of n squared plus 1 minus 1. But every time you have these things, we have seen this in class as well, you multiply and divide by the square root of this plus n. Okay, so then you have the square root of n plus 1 minus n times the square root of n squared plus 1 plus n divided by the square root of n squared plus 1 plus n, right? And in the numerator you have a minus b times a plus b, which is equal to a squared, okay, n squared plus 1 minus n squared, okay? So this is equal to 1 over the square root of n squared plus 1 plus n, right? And now we can use the limit comparison test and say that the square root of n squared plus 1 plus n is asymptotically equivalent to 2n, right? Because this is asymptotically equivalent to n, so 2n, okay? So this series with this general term is asymptotically equivalent to this, but this is 1/2, so the series of this is 1/2 of the harmonic series, right? Again, and this is divergent, so the two series, the general term for the two series is asymptotically equivalent, which means that two series are divergent at the same time. Okay? Okay, let's do 15. The sum from n equals 2 to infinity of 1 over n to the logarithm of n. Okay, so let's see. This is not obvious, okay? But what I can say is that we know that the logarithm of n, right, is going to be greater than 2 for some n, right? For n greater than, let's say, 10, for instance, right? So the logarithm of 10, I think it's going to be greater than 2. So we can apply this comparison test for this kind of like less strict comparison test in which the comparison of two sequences is not strict for all terms but up to some point. Okay, but this is okay if it starts in n and greater than 10, then this is good enough. Okay, so now if the logarithm of n is greater than 2, then n to the logarithm of n is greater than n squared, right? But in other words, this means that 1 over n squared is greater than 1 over the logarithm of n. We know that the series of 1 over n squared is convergent. So because this term is bounding this term from above, we know that this series will be convergent as well. Okay, so this is an application of the comparison test. Okay, okay, let's do 16. 16 is the sum from n equals 2 to infinity of 1 over the logarithm of n to the logarithm of n. And now this is clearly one in which we need to apply Cauchy's condensation test. Okay, so we need to say we have a sub n is 1 over the logarithm of n to the logarithm of n, and now we have to remember 2 to the k, a 2 to the k, right? And so we have 2 to the k divided by the logarithm of 2 to the k to the logarithm of 2 to the k, which is equal to 2 to the k divided by, and then we have k, the logarithm of 2, and then we have 2 to the k logarithm of 2. Well, let me write it here, right? So we have 2 over k logarithm of 2, all of this to the k, right? And then divided by 1 over k to the logarithm of 2 and the logarithm of 2 to the logarithm of 2. Okay? And now, so we need to check the convergence of this series, right? From k equals 0 to infinity of, let's see, 1 over k log 2 to the log 2 times, and then 2 to the k logarithm of 2 to the k, right? We need to check this convergence. So let me erase this part. And in order to check the convergence of this, we have something that's to the k. So we use the root test. Okay? The root test for this is the limit, and let's use k, okay? When k goes to infinity of a sub k, the kth root of this, then we have the limit when k goes to infinity of the kth root of all of this. So we have 1 over the kth root of k logarithm of 2, all of this to the logarithm of 2. But we know all of this is going to be 1 times 2 over k, the logarithm of 2, right? So this is going to be 1, and then this is going to 0 because we have 1 over k, right? So this is going to 0. This is smaller than 1, so that means this series is convergent. But if this series is convergent, then the original one is convergent. Okay? It is kind of convoluted, but I hope that you see the videos correctly. Sorry, the videos, sorry about that. The idea, right, of the yes, the argument. Sorry about that. Okay, let's do. We are almost there. 17. Okay, so let's do 17, and we are almost there. Okay, this is the sum from n equals 1 to infinity of 1 over n times the nth root of n. Okay, here it's not obvious. Okay, obviously we can't use the root test. Okay, the root test is for when you have something to the n, but here we have something to the nth root, right? And the quotient test doesn't look very good, right? But what we know is that the nth root of n will go to n, to 1, sorry, okay? So that means that the n times this is asymptotically equivalent to n, okay? Because yeah, you have the limit when n goes to infinity of n times the nth root of n divided by n. You have the limit of the nth root of this, and this is 1. So these two things are asymptotically equivalent. So 1 over n times the nth root of n is asymptotically equivalent to 1 over n. But 1 over n, the series of 1 over n is divergent. So this means that this one is also divergent. Okay, so using the limit comparison test, right? And then 18, which is the last one. 18. We have the sum from n equals 2 to infinity of n over n minus 1 to the n. Again, the series starts at 2 because if when n equals 1, this is 0, so this fraction is not defined, right? Well, if you use the root test here, this is interesting because the nth root of a sub n is a n over n minus 1. The limit of this is 1. Okay, so the root test is not deciding. Okay, if you use the quotient test, you have the limit of n when it goes to infinity of a sub n divided by a sub n minus 1. What you have is the limit of n over n minus 1 to the n, and then divided by n minus 1 to the n minus 1 times n to the n minus 1. Okay, and again, if you do this, you have everything. It's n divided by n minus 1 to the something. Or wait a minute. Let's see. You have the limit when n goes to infinity, and then sorry, this is not n. Sorry, this is n minus 2 to the n minus 1, right? And if you do this, what you have is n times n minus 2 divided by n minus 1 squared, all of this to the 2n minus 1. Okay? And so this is one of those, let's see, e to the c, right? This is, the limit of this is, let me write it here. The limit when n goes to infinity of a sub n over a sub n minus 1 is n squared minus 2n over n squared minus 2n plus 1. Okay? So this is the limit of this. When this is to the 2 to the n minus 1, right? And you could see that this is also 1 minus 1 over n squared minus 2n plus 1, okay, to the 2n minus 1. So this is some clearly 1 to the infinity, so the limit now is some kind of e to the c, and we need to find c, but c is the limit when n goes to infinity of minus 1 over n squared minus 2 plus 1 times 2n plus 1, sorry, minus 1. And the limit of this is 0, right? Because the degree of the denominator is greater than the degree of the numerator. So then you have e to the c, which is 1. So again, the quotient test does not decide, okay? The root test does not decide, the quotient test does not decide. So what do we know about this series? Okay, it's actually much easier in this case. Why? Because the limit when n goes to infinity of n over n minus 1 to the n is the limit when n goes to infinity of, and then this is n minus 1 plus 1, okay, over n minus 1. So this is 1 plus 1 over n minus 1 to the n. The limit of this is e. So the limit of the general term is e. That means that, you know, after so many, you know, when n is very large, this term is very similar to e. So just summing e an infinite number of terms. So this means that this series is divergent because the general term is not converging to 0. Okay, so that's the basic test. Okay, and that's the thing you should always test at the beginning when you start to test these things. Okay, if it doesn't work. Okay, so that ends problem 4.1.